Welcome to the fifth lecture in Applied Math. The topics that we'll explore in this lecture include an introduction to homomorphisms and isomorphisms, and we'll continue where we left off in the previous lecture looking at the point groups of molecules. Okay, so we'll start with the exercises from the previous lecture. So first, let G be a group and let A be an element in the group. Then the set of all integer powers of that element A is a cyclic subgroup of the group G, and in fact we call this the cyclic subgroup generated by the element A. So proof. First, notice that this set is a non-empty subset of the group G, since it contains at least one distinct element, the element A. So let G sub 1 and G sub 2 be two elements in this non-empty subset. Then there exist integers m and n such that G sub 1 is equal to a to the power of m and G sub 2 is equal to a to the power of n. And so G sub 1 times the inverse of G sub 2 is a to the power of m times a to the power of n to the power of negative 1, which is a to the power of m times a to the power of negative n, and this is a to the power of m minus n, where m minus n is an integer, and hence for every pair of elements, G sub 1 and G sub 2, in this non-empty subset of the group G, the product of G sub 1 and the inverse of G sub 2 is also an element in this non-empty subset. So by the previous theorem, which we proved in the previous lecture, this non-empty subset is a subgroup of the group G. And further, this group is cyclic by definition, and therefore the set of all integer powers of the element A is a cyclic subgroup of the group G. Okay, so next, let pi be the permutation that maps 1 to 2, 2 to 4, 3 to 6, 4 to 1, 5 to 3, and 6 to 5, where pi is an element in the symmetric group on 6 letters. First, we'll look at the digraph for this permutation. So 1 is mapped onto 2, 2 is mapped onto 4, 3 is mapped onto 6, 4 is mapped onto 1, 5 is mapped onto 3, and 6 is mapped onto 5. So notice that this digraph shows two disjoint cycles, so we can represent the permutation pi in cyclic notation as the pair of disjoint cycles, 1 to 2 to 4, and 3 to 6 to 5. Notice that each of these cycles is of length 3, and so pi has 0 cycles of even length, and therefore pi is an even permutation. Since it has an even number of even cycles, since 0 is an even number. So next, we will write the elements of the dihedral group of order 8 as permutations of the 4 vertices In fact, we'll write it in cyclic notation. So first notice that the rotation rho is rotation by 360 degrees divided by 4, or 90 degrees counterclockwise about the vertical line through the center O of the square. So we begin with a square, and we'll label the vertices as follows. Then one rotation by 90 degrees counterclockwise produces the square with the vertex 1 exchanging places with 4, vertex 4 exchanging places with 3, vertex 3 exchanging places with 2, and vertex 2 exchanging places with 1. So that the rotation rho can be expressed in cyclic notation as the cycle 1 to 4 to 3 to 2. Now, if we follow this by a second rotation of by 90 degrees counterclockwise, then notice that vertices 1 and 3 have exchanged places, and vertices 2 and 4 have exchanged places, and so we can write the permutation rho squared as the pair of disjoint cycles 1 to 3 and 2 to 4. And if we follow by a third rotation counterclockwise, which is equivalent to rotation by 270 degrees counterclockwise, then notice that the vertex 1 has exchanged places with 2, 2 has exchanged places with vertex 3, 3 has exchanged places with vertex 4, and 4 has exchanged places with vertex 1 as compared to the original, so that rho cubed is the cycle 1 to 2 to 3 to 4 and back to 1. And rho to the fourth power, that is rotation by 360 degrees, leaves the square in its original configuration. So this is the identity permutation, which we can represent this way. Now, mu is the reflection about the line or vertical plane through the center O of the square and the first vertex. And so again, beginning with the square in its original configuration, if we rotate, or rather reflect, the square about the line through the center and the first vertex, which also passes through the third vertex. Then vertex 1 and 3 are fixed, and vertices 2 and 4 exchange places. So we can write the reflection mu as the cycle 2 to 4. If we follow this reflection by a rotation of 90 degrees counterclockwise, then notice that vertices 1 and 4 have exchanged places, and vertices 2 and 3 have exchanged places, so that rho times mu can be written as the pair of disjoint cycles 1 to 4, 2 to 3. If we follow by a second rotation counterclockwise 90 degrees, then notice that vertices 4 and 2 have remained fixed in relation to the first or the original square, and that vertices 1 and 3 have exchanged places. And so we can write the reflection symmetry, rho squared times mu, as the cycle 1 to 3. And if we follow by a third rotation counterclockwise, then notice that vertices 1 and 2 have exchanged places, and vertices 3 and 4 have exchanged places, and so the reflection symmetry, rho cubed times mu, can be written as the pair of disjoint cycles 1 to 2 and 3 to 4. And so the reflection symmetry, mu, is equivalent to reflection about the line through the center of the square and the first vertex, which also passes through the third vertex, so that 1 and 3 remain fixed, and 2 and 4 exchange places. The reflection symmetry, rho times mu, is equivalent to reflection about the line through the center of the square that passes through the midpoints of the opposing or opposite sides, the sides containing the vertices 1 and 4 and 2 and 3, so that 1 and 4 exchange places and 2 and 3 exchange places. The reflection symmetry rho squared times mu is equivalent to reflection about the line that passes through the center of the square and the second vertex, which also passes through the fourth vertex, so that vertices 2 and 4 remain fixed, and vertices 1 and 3 exchange places. And finally, the reflection symmetry, mu cubed, or rather rho cubed times mu, is equivalent to reflection about the line that passes through the midpoints of the opposite sides containing the vertices 1 and 2 and 3 and 4, so that 1 and 4 exchange place, so that 1 and 2 exchange places and 3 and 4 exchange places. So let's look at the consolidated elements of the dihedral group of order 8, we have 4 rotation symmetries. Rho to the 4th power, which is rotation by 360 degrees. This is the identity permutation, which we represent this way. Rho, which is the rotation by 90 degrees counterclockwise about the center of the circle. And this is the cycle 1 to 4 to 3 to 2. Rho squared, which is rotation by 180 degrees counterclockwise about the center. It is equivalent to the pair of disjoint cycles 1 to 3, 2 to 4. And rho cubed is rotation by 270 degrees counterclockwise. And this is the cycle 1 to 2 to 3 to 4. There are 4 reflection symmetries. Mu, which is the cycle 2 to 4. Rho times mu, which is the pair of disjoint cycles 1 to 4, 2 to 3. Rho squared times mu, which is the cycle 1 to 3. And rho cubed times mu, which is the pair of disjoint cycles 1 to 2 and 3 to 4. So notice that the rotations alone, consisting of identity, rho, rho squared, and rho cubed, is the cyclic subgroup generated by rho. And so the cyclic subgroup generated by rho is indeed a subgroup of the dihedral group of order 8. So now let the set S be the set which contains the identity, rho squared, mu, and rho squared times mu. We'll look at the Cayley table for these 4 elements. That is the multiplication table. Now rho squared times rho squared is rho to the 4th power, which is the identity. Rho squared times mu is the element, rho squared times mu. Rho squared times rho squared times mu is rho to the 4th power times mu, which is identity times mu, so this is simply mu. Now mu times rho squared is the cycle 2 to 4 times the pair of disjoint cycles 1 to 3, 2 to 4. So beginning with 1, 1 is mapped onto itself in the first cycle, and then onto 3 in the second cycle, and in the third cycle 3 is mapped onto itself, and so we have the cycle 1 to 3, beginning with 2, 2 is mapped onto 4, 4 is mapped onto itself, 4 is mapped onto 2, so 2 cycles out, and beginning with 4, 4 is mapped onto 2, 2 is mapped onto itself, and 2 is mapped onto 4, so that 4 cycles out, and so this is the cycle 1 to 3. Notice that this is the same as rho squared times mu, so mu times rho squared is rho squared times mu. Mu times mu is mu squared, which is identity, and mu times rho squared times mu is the same as mu times rho squared, which is mu squared times rho squared, which is rho squared. Rho squared times mu times rho squared is the same as mu times rho squared times rho squared, which is mu times rho to the 4th power, which is mu times identity. So we have mu. Rho squared times mu is rho squared times mu squared, which is rho squared times identity, which is rho squared. And finally, rho squared times rho squared times mu is the same as mu times rho squared times mu, which is mu times rho to the 4th power times mu, which is mu times identity, times mu, which is mu squared, which is identity. So notice that this set is a non-empty subset of the dihedral group of order 8 that is closed under the operation of multiplication, which is equivalent to composition of functions, and that this set contains the identity, and that for every element in the set, every element in the set is its own inverse. And so by the previous lemma that we proved in the previous lecture, this set S containing the elements the identity, rho squared, mu, and the product rho squared times mu is a subgroup of the dihedral group of order 8.